last time we were talking about how to measure objects and how each measurement is affected by an error. We also saw the difference between absolute and relative error. And then we also saw some of the major units of measurement. Then I also attempted to explain orders of magnitude with not so much luck, unfortunately. Okay, so today we are going to continue our overview of the main concepts of physics, and we are going to focus on force particularly.
Good. I remember also that last time you has spoken about the dimension, about mass.
Oh yeah, the units.
I think that it's very important.
Yes.
In common language, we don't focus very well about this really three fundamental dimensions. Okay, Francesco.
Okay. Is it something I have to elaborate, or can I just move on? Okay. So today we are going to focus on force. Now, it is kind of hard to actually explain what force is, because it can come in many different shapes. So, if, for example, you are pushing an object, you are applying a force on it. If you put two magnets next to each other, they're going to apply a force and either come closer or repulse each other depending on their polarity. Also, the Earth itself can apply a force to any object, which is the so-called gravity force. So since there are so many types of force, it's hard to give a precise general definition of it. There is one characteristic that we can focus on. And it's that if you have a static object, one that it's still, and say you push it, you are going to apply a force to it, and as a result your object will move. Okay. Similarly, if you have a moving object and you touch it to stop it, your force causes that object to stop moving. And if you have an object that's moving in some way, you can apply some kind of force to make it move in some other way. So essentially, you can define a force as anything that can cause a still object to move, a moving object to stop, or a moving object to change its motion. Okay? Now,
le puoi scrivere? Le puoi scrivere le tre manifestazioni, diciamo?
Okay, also there is a force type of effect that you can have, and that is if you have some kind of object like a plastic bottle, you can use a force to apply a deformation to it, like when you crush it with your hand. So this is not related to stillness or motion, but it's still an effect of a force. Okay. So we will be studying motion in a few lectures. Today we're going to focus more on the force effect, the deformation. So have you all seen a spring before? Okay. Have you all seen something like this? Okay. So a spring is a kind of object such that if you apply a force to it, it will deform and then return to its original state once you once you let go of it. This ability of returning to its initial state is called an elastic behavior. And do you know how the more you try to stretch a spring, the harder it becomes to stretch it further? That is because as you try to stretch the spring, it will apply another force that tries to return it to its original state. This is the elastic force. Okay. So if you have an elastic object and you deform it, you have this force that will try and return it to its original state. Of course, there are limits. After a certain point, you can break the spring, but that's out of the question for now. And the interesting thing is that there is a very simple law that determines how much this force is exactly. So if you have a spring such that its normal length is L0, we also call this length at rest. In general, when we say at rest, it means that it's still with no influences on it. So you have a spring that has a certain length at rest. Then you can apply a force to it, and it will become stretched. So its length will become something else, L1. What we take note of is the difference in length, or the stretching, which we call delta L. And there is a simple physical law that relates the force you apply with the stretching you get. And it might actually be familiar to you because it's simply, let me make sure I get, yeah. It's simply this. With force, stretching, and this which is called elastic constant. Constant because this value will not change, and it basically depends on the physical characteristic of your specific spring. So this represents how easy or hard it is to stretch this specific spring you are working with. So, does this form look familiar to you?
It's actually familiar, but not in this form. Like maybe another thing instead of K or delta L, another name of in English. That's what I think. But about the delta L, I didn't heard about it before.
Okay. Let's say I was talking less about this specific formula and more about its form. Like you have two quantities in this specific relation.
Ah, yeah, it's familiar. Yeah.
Yeah. So, as I think Fatima has seen, you can notice that the force you apply and the resulting stretch, or if you will, your desired stretch and the necessary force you have to apply to get it are in direct proportion. So if you apply a certain force and get a certain stretching, if you apply double the force, you will get double the stretching. Note, I am still talking about stretching, not about your total length. Okay. And this rule has a name. It's called Hooke's law. Where Hooke is just the name of the guy who discovered it. Is it all clear until now?
Maybe, is it clear for you?
Yes, it is.
Yes. Okay. Sima, do you remember direct proportion? Yes. Direct.
These kind of things are so new for me. I've never had it before,
Yes,
but
physics,
yeah, it's good.
yes, direct proportion.
Okay.
This is it.
So essentially that, okay. So I will make a practical example so that we can see both this rule in action and also explain that direct proportion for those who haven't seen it so often. So I will rewrite our rule here. So say that you have a spring whose elastic constant is like 3. Oh, by the way, also this quantity, the elastic constant, has a unit of measure. Which would be Newton over meter. When you're working with constants like this, I find it easiest that in order to remember which unit of measure it is, you can just look at the law itself. So you have a force, which is Newton, and here a stretching, which is still a kind of length, so it's meter. So what would you need here in order? So what is that multiplied by meter gets you Newton? You just take meters over here and get that whatever you want, and get that what you need is Newton over meter. Okay, that's it. So you have this specific spring that has an elastic constant of 3 Newton over meter. So say that you are applying a force of 9 Newton. What is your corresponding stretching? It is, you just take the K here and bring it to the other side. It will be force over constant. So 9 Newton over 3 Newton. Okay, so 9 Newton over 3 Newton per meter. You will get 3 meters of stretching.
Is it clear, the formula?
Yeah,
Okay.
Okay,
for me it's clear.
good. Good.
Okay. Yeah. was thinking to, yeah, okay, never mind. So now say that you apply a force that is double this. Your stretching here is still force over constant. Remember that K never changes unless you are working with a different spring. So this time 18 divided by 3 will be 6 meters. And notice, Sima, that it is double the stretching from before. So this is what direct proportion means. If you double one quantity, you also double the other, etc., etc. If you triple the force, you also triple the stretching. If you triple the stretching, you also triple the force. If you halve one, if you divide by half, you also divide by half the other, etc., etc. So okay, so let's do another example. Let's say that you are still applying 9 Newton, but this time you are working with a different spring, which will have an elastic constant of 5 Newton over meter. So what do you expect to change for the stretching? Will it be more or less than the 3 meters we got here?
I think it's going to be less than 3, less than that we did it before.
Exactly. So we have still 9 Newton, but over 5. Should be 1.8. Yeah. So you get a smaller stretching. So for the elastic constant, a high constant means that your spring is stiffer. It's more rigid. Okay. Okay.
What does it mean?
Huh?
What rigid means here?
What?
What the meaning of rigid? What's the meaning?
It's hard. It's harder to stretch.
Mhm.
Stiff, rigid, hard, they're all synonyms. They all mean the same thing. While a lower K would mean that you have a softer spring. Okay, so we have gone over force in general and over a elastic force and Hooke's law, and also over the elastic constant. Okay, and by the way, you can also use this law to build an object, to build an instrument that will measure force. So say that you have a ceiling here with a spring hanging from it, and that here you have a ruler with which you can measure stretching. Then, if you hang a weight on the spring, you will cause it to stretch. And by measuring on the instrument your stretching, and knowing the constant of your spring, you can compute the force and thus have an indirect measurement of the force. This kind of instrument, I think it's translated as dynamometer, I think. And it's one of the ways you can use to measure force. Okay, I think we can do some exercises now on this. So let me see. Okay, let's start with a simple one. So you have a spring whose elastic constant is 100 Newton per meter. And you apply a certain force such that it will stretch by 2 meters. So what would the force be? As a reminder,
200.
exactly 200.
And with the measure, we are gonna write m square also, or no? We don't need it.
Well, it's 100 Newton per meter multiplied by 2 meters. So
Then it will be just
so
Newton.
yeah.
Yeah.
So meters will cancel out, as though it basically works as though they were letters in in an equation. Also note, a force is always Newton. If you do some calculations and you end up with a force that is not measured in Newton, you are doing something wrong. So yeah, you have 200 Newton. Okay. Now for something a little more complex. So when you're doing physics exercises, it's also common to sketch the situation. So here we have a spring that has a constant of 120 Newton over meter. And it has a certain length at rest of 45 centimeters. Then this same spring is applied a certain force. Oh, that's the unknown. And you observe that its length changes, of course, and it has now become 60 centimeters. And so you want to know what force is being applied. Now, before we begin, you have to do something very important, and that is to make sure that your units match. So here you have length measured in centimeters, but your K is still in Newton over meter. So it's very, very important that you convert your length in meters. In general, always make sure that you have everything in the base units. So meters for length. So So if you have centimeters, you convert to meters. If you have kilometers, you also convert to meters. Then for masses, it's kilograms. So if you have grams, make sure that you convert. For time, it's seconds, etc. For everything else. Make sure that you always make sure that you always convert to the base units. So here, for example, "45 centimeters" will be 45 divided by 100. And 60 centimeters will be 60 divided by 100 meters. So you'll have that L0 is 0.45 meters and L1 is 0.6 meters. Okay. That said, since this is our first serious exercise, I would go over it now. Okay. So, as a first thing, we note that here we are given full length, but you have to remember that Hooke's law works over stretching. So before you proceed, you have to calculate the stretching given by this starting and final lengths. So if you have the final lengths and the starting lengths, the stretching will just be the difference. Do you all agree with this?
Yeah.
Okay, so in this case, that would be 0.6 minus 0.45 meters. So that would be 0.15 meters. After that, it's just a direct application of Hooke's law. You have 120 Newton over meter multiplied by 0.15 meters. Which will be 18 Newton. Okay. Do you have any questions?
Yes, I have. For the, it is 45 meter. Why it isn't? Because I calculated 4 and I don't know what is English. 4 and 5, not 45.
You mean 4.5? This? Sima.
Yeah.
Okay.
Yeah, yeah.
So let me make a new page. So the problem says that the starting length is 45 centimeters. Sorry, 45. 45 centimeters. Okay.
Yeah.
Now, by definition, a centimeter is a part of a meter, specifically such that 1 meter is 100 centimeters. Or conversely, 100 centimeters make 1 meter. Okay? So if you invert this relation, you divide both sides by 100. You get that 1 over 100 meters is 1 centimeter. Then, if you want, you just take, think that centimeter is just another, just like a letter in an equation. 1 multiplied by centimeter is still centimeter. Then you can take centimeter and substitute here. So you will end up with L0 being 45 multiplied by 1 over 100 meters. And so that will be 0.45 meters.
Okay.
Okay.
Mm-hmm. And one more question.
Mm-hmm.
Why do we should 45, 100 and 600, we should make it minus. I mean, we should do the minus, not the take it together. Because I did it, I take these two together and my Newton is 612.
Okay, so you're asking, let me make sure that I got this question right.
Okay.
We have 2 lengths. So you're saying, why is delta L this, L1 minus L0, and not this, L1 plus L0? Is this what you're asking? Why is it not this?
Yeah.
Okay. So just think of it graphically. So you have a spring. Now let me replace the spring with a simple line so it's easier for me to draw. Okay. So
okay.
You have this spring, and so it has no force applied to it. Its length is L0, okay? Then you apply a force to it. Your spring stretches. its length is now L1, okay?
Mhm.
Now, if we now delete the springs and just keep our lengths, okay? Then I'm also going to show this horizontally, okay? This is our same situation, but it's horizontal rather than vertical, okay?
Okay.
Now, would you agree that the change in length from this to this is this line I drew in red?
That line.
Yeah. So
Yeah, this.
the amount that the
Same.
yeah. So the amount that the spring stretched is this. Okay. Is it clear, or do I start over in a different way?
No, it's good. Yeah, I understand.
Okay. At this point, it should be easy to see that L0 plus delta L is L1, right?
Yeah.
Therefore, you just take L0 the other way. Delta L will be L1 minus L0.
Okay.
To put it in another way, I'll let you finish writing. Okay. So here we are using the minus sign because we are making a comparison. So we know the initial state, we know final state. We are comparing them. We want to know how much this changed. Okay.
Okay.
Measuring changes as a difference is going to come up more times in physics. So whenever you want to see a change in something, or a variation, if you will, you are gonna use the minus sign. And generally, not always, but generally, use delta to signify change or variation. So most of the time you see a delta, that's gonna be a difference between two states. There might be exceptions, but most of the time it'll be this. Okay. So, does anyone have any more questions for this?
No, I don't have any question.
Okay, Mari as well, is it clear?
Yes, is it clear?
Ok,
Possiamo fare l'esercizio da sole, che dici?
sì, infatti. So, now I would like you to do something similar
Facciamo
by
una semplice.
yourselves. Mhm.
Ma semplice, no?
Yeah. This will be pretty much the same thing. So we have a different spring that has a constant of 25 Newton per meter. No, it is. Okay. Its default length will be 18 centimeters. After you apply some force, its length will be 22.5 centimeters. And we still want to know the force that it's subject to. Okay. So you can try and do this for yourselves.
So I got an answer.
Mhm.
I actually turn all of them into meter. Should
Okay.
I say everything? Yeah.
Yeah.
And then, so I got 0,18 meter, and then another one is 0,255, I think, yeah, meter. And then
You mean 225?
225
Yeah.
meter.
Okay.
Yeah. Then I just minus each other to have the different
Okay.
together. So I got 0,045.
Mhm.
Then I actually just multiplied to 25. So I got, I don't know, I'm not sure if I didn't just mix up anything. So it's 1.125 Newton.
And that's right, actually.
Yeah, good.
Okay. So, yeah, this was pretty much the same as before. So I assume you don't have any questions for this.
Sima and Martin?
Yeah,
Yeah. Sorry, Sima.
I want to say yes. I got also this answer that Fatima has it.
Okay.
Can you hear me?
Yes.
Yes.
Hello.
Yes.
Yeah. I want to say that I take this. That's
now we can't hear you. We couldn't understand what you said.
right now. Is it? Can you hear me? Because I can hear you, but I'm not sure. Do you guys hear me or no?
We can mostly
Hello?
hear you. Yeah, now we can hear you.
Mm-hmm. Now, yes.
So what were you saying before?
I said that I take this answer also that Fatima has it.
Okay.
1.125 Newton.
Okay.
Good. And Mommy?
I got it the same thing.
Okay, great.
Good. Very, very good. Well.
So if you're okay with it, I would like to show you one last exercise, which will do something a little different. So we have the same situation again. Your starting length is 20 centimeters. The final length is 22 centimeters. Oh, yeah. Centimeters. Centimeters here, centimeters there. You have a force of 2.5 Newton. This time what you want to know is what is the elastic constant of your spring.
Good.
I have the answer, but it's 125.
Yeah, that is correct.
Very quickly. Very, very quickly. Sembra che i concetti ci stanno tutti.
Sì. Ok. Yeah.
Bene.
Okay.
Very good.
So I'm going to wait for the others too.
Yes.
I got it, but I think it is incorrect because mine is 1.4.
Okay.
Why?
Vabbè, più o meno, dai.
Beh, più o meno proprio tanto. Do you want to tell me what you did, Sima?
Yeah, I got L1 minus L2, L0, and I got 20 centimeter, and I make it
No, wait. Can you repeat?
L1 minus L0, and
Okay.
I got 20 centimeter.
So you're saying that you did 22 minus 20 and you got 20?
Yeah. Yeah.
Okay, but
L0, is it?
Okay, but keep in mind that that 22 minus 20 is 2.
Sima, are you sure that?
Oh my God. Yeah.
Yes.
Oh my God. Yeah.
Okay.
Oh my God.
Another thing is that you can do this operation first, but remember that your result will still be in the same unit as the one you had before. So if with these data in centimeters you do this difference first, you can do it, but your result will be in centimeters. So you will have to convert it in meters before you can move on and compare it with the force in Newton. Okay?
And we got 0.02 meter.
Yeah. And okay, do you want to go on and get K as well?
Okay, and we have the F. F is 2.5. So 2.5 divided by 2 is 200 meter.
It is
I don't know.
it is 0.02. Remember from before, 1 centimeter is
This
0.01 meters, which is 1/100. So 2 centimeters will be 0.02 meters.
So we do the division.
Yeah. It is division.
Division, yeah.
Yeah, because divide is the verb and division is the
Division
is the corresponding noun. So yeah,
and
for that you just have to use a calculator.
Mahbub,
2.5 over
Yeah.
0.02 will be 125. Okay. And Fatima, how's it going?
Yeah, it's nothing. I just got the answer, the same answer.
Okay. Okay.
No,
So-
no answer, no question.
Okay. So I see that you have no problem using derived formulas.
Yes.
So getting here from the basic formula.
Mm.
Okay. Great.
Non so se vogliamo lasciargli qualche esercizio da fare per conto loro. nei prossimi giorni.
Sì, purtroppo il libro ce l'ho in italiano, chiaramente. Dovrei cercare qualcosa.
Vediamo. Vabbè, magari vediamo non ora, però
Mhm.
certo.
Okay, I'm going to look for some exercises that you can do over this week. Okay, now I wanted to go over one last concept. It's a simple one, and it's pretty separated from the rest. So we are going to go very quickly over the difference between mass and weight. So do you know what your weight is? What your weight is?
Yeah,
Okay, can you tell us?
I'm 46.
Okay, 46 what though? We have just said that everything.
46 kilo.
Okay,
Oh,
okay,
I think it's a little low, but fine.
okay,
I'm sporty.
no.
okay. So regardless of the specific number, I asked you for your weight, and you answered me in kilograms,
Mm-hmm.
because that's what we colloquially mean. But if you remember from yesterday, I told you that kilograms are the unit of mass.
Yeah.
So while in common language we use mass and weight as the same thing, in physics they are completely different. And actually, let me start by saying that kilograms are for mass, not for weight.
Okay.
Weight by weight, what we actually mean in physics is the force that is basically the force of gravity. As such, weight is measured in Newton because it's a force. There is another simple relation between mass and weight, and it is that the weight is equal to mass multiplied by g. So g is a constant that you will come to know very well. It's called gravity constant.
Yes.
And to put it simply, it depends on what planet you are in. On Earth, it is 9.81 meters per second squared, because it's actually an acceleration.
What's there? Like meter over what?
Meters over second squared.
Second squared. Okay.
Yeah, this S is like this S. I will just as often write with this other S. They're just both S. Okay, that's it. So, for example, Fatima's mass is 46 kilograms. Her weight on Earth would be 46 multiplied by 9.81, 46 kilograms multiplied by 9.81 meters over second squared, which will be 451.26. Yeah.
Too much.
Yeah.
Bene.
And by definition, this thing is a Newton.
Okay.
So rather than saying that force is kilograms by meters per second square every time, we just call it Newton and make it short.
Okay.
So weight is defined as the force that whatever planet you are in is exerting over you, while mass is more like the quantity of matter that is in your body.
Okay.
So your mass is is always constant. Well, actually, the mass of a human changes for reasons unrelated to what we're studying. So, so taken any object, its mass will always stay the same, but its weight can change depending on its location. So if you have a weight like those you use in a gym, whose mass is 1 kilogram, it's always 1 kilogram anywhere it goes. But on Earth, its weight will be 9.81 Newton. And I have no more space, but if you take it on the moon, for example, it will always be 1 kilogram, but its weight will be different. It will be less. Okay.
Yeah, what's the gravity constant in the Earth, in the moon?
We'll have to look for it.
It should be lower, yeah?
Yeah, it's much lower. Yeah, I think we can say it's 1.6.
1.6.
So since we have just 1 kilogram of mass, its weight would also be 1.6 Newton on the moon. So so you see it's much less. Okay. So that's it for today.
Is it difficult? No. No.
No, it was more actually funny for me. Because we did, like, we use it in everyday our life.
Yeah. Yeah, that's the beauty of physics in a sense.
Well, okay.
Okay, so to do, if you don't have any more questions, thank you for your attention, and we'll see again next week.
Thank you very much also for the lesson.
Okay.
Yeah. And have a good week.
Yeah,
Thank
you too.
so much. Also for you.
For today.
Ciao.
Okay. Bye.
Bye. Ciao Francesco,
ciao.
grazie.
Ciao.
Ciao. Ciao, ciao.
Bye bye.
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 Ciao.
Bye.
Ciao.